Okay. We're back live. Hello. I got a little bit more work in me, I think, tonight. Just a little bit. See if I can get this. The backward kernel is actually going to be faster than the forward kernel, isn't it? Gate grad hidden. Grad. Yeah, where's the buffer? I normally do buffers. Yeah. This is the template. This will just be grad out. And then this is in out buff. Norm buff. Like this, right? Okay. So do float in norm. Norm buff. It's actually really easy from here, isn't it? You actually just go int h. And then we just do out times inverse norm. I think this is literally it, right? Isn't it just this easy? I believe it actually is, because yeah, the only thing that's difficult about this is this reduction up top, right? So then actually we can do, can't we just launch the backward kernel? We can totally just launch the backward kernel differently, right? Oh, okay, so then this is norm idx equals idx divided by h, I believe. The percent h. Times, it's something like this. Right? Oh, wait, no. Neural nets from scratch in PyTorch. Oh, in Python. I don't know, man. All my best, like, beginner stuff is on Twitter. If you just click my articles tab. These two. This. How does one spell shenanigans? Wait, you need grad with respect to the weights and grad with respect to... Yeah, hang on, I'm done. This is grad... the x... grad weight, right? So this is grad... grad with respect to the weight. Grad x. And then times 2. Wait. How's this weight work? Well, I'm just implementing this stuff totally wrong, aren't I? I'm like forgetting that it has a weight. Yeah. Okay, we'll figure this out then. Gamma I. Yeah, so it has to be times weight. The heck is W? W. W times this. Do you still publish papers? No, but I write blog posts and all my stuff's open source. I did just publish the last planned paper at the very least is PufferLib 2 is in RLC. I need to put that up on the website because it got an award, but anyways. What is wrong with this? Enter base. Is there no base? Base plus H. What's the LSP like show? Whatever. That later. Okay, let's actually do this correctly. So, what's the gradient of this? Gradient of this with respect to W is just this whole quantity, right? Xi over in norm. This. Right? And then gradient with respect to this is isn't it like double check something. I think it's like 2. But it's probably not actually. And of weighted form. You have an epsilon by default? No. Oh, this does actually have an epsilon. I see. It does have an epsilon. What on earth is... What is R? Fuck is this R cubed? R, right? Oh no, it's epsilon. Interesting. I guess, yeah, that is actually a non-trivial gradient. I forgot. Don't use AI for coding. As little as I can, man. Every fucking time I regret it. And here it's like, I'd rather just ask it for the math than ask it for the code. But then I don't even trust it to do the math. Dude, it's literally a meme. Like, I had some other guy tell me, oh, just try Claude or whatever. I typed the same shit in, and they're all just dumb, alright? They're all stupid. Let me at least check this manually. This is epsilon. Okay, this is the correct form. R equals R mass of X equals... Yeah, okay. Oh, okay, so this was defined to be the RMS. Cool. Gradient of a single output element. If I equals J. Huh? Oh, do you actually get cross terms here? You do, don't you? Ugh. I forgot about that. I completely forgot about that. Non-reasoning version? I've tried both. They all suck. And also, this is just 4.1. This is just how they have it by, set up with 4.1. You do actually get cross terms here, don't you? Yeah, I totally forgot about that. Right? Because normally you don't have operations that do this. Yeah, okay. So let's check this first. So this is respect to x. The summation. It comes from the norm, right? Like the fact that you're dividing by the sum of the other elements. Okay, so this is 1 over... This is wi. xi. Single element. I don't have to do math all that often. It's like... Give me a moment here, alright? Let me remember how the hell this works. Okay, so it went through this op for some reason. Yeah, it's just not showing where it got this. Let me see. So RMS of X. 0.5 to the negative 1/2, or am I wrong? Yeah, I literally do not remember how to do this. Yeah, because I have to write out, it's kind of crazy, but literally the RMS norm operation, which should take no time. Yeah, that one operation is taking like 25% overhead. I suppose I can try this gradient to see if this gradient is correct, because I can test it. Let's try this one, and we'll assume that this is correct for now. Let's get this to actually compile. Because the grad with respect to weight is just, it's trivial, right? It's just this. So then this one is actually going to be... and actually we want the weight. Float W. Float G. Equals out. Oh, and you need the input buffer as well here, don't you? Yeah, you need the input buffer. Is this how I did it? A buff, S buff. Oh yeah, I just don't have it in here. Cool. I'm not really using tags. This is Super Maven, which I'd be very happy to keep using, but Cursor being the dog shit company that they are, they said that they were like getting rid of it, unless they canceled that suggestion. I mean, unless they canceled the closure. If so, major props. Oh, nope. Oh. Free autocomplete inference for existing customers for the foreseeable future. Wait, what? Oh. Oh, I see. Did I like miss this whole thing? There you go. Props where they're due. Good job. So I guess I get to keep using my autocomplete. Yay. Do you need to code the gradient manually for the kernels? I need to code the gradient for the kernels manually because PyTorch is too damn slow. That is what we're doing. This is ultra high performance RL optimization. I thought you have like trained Bert. Nope. Oh. Thank you. Hey. Ice cream delivery. Apparently my family went to Dairy Queen while I was here coding. I mean, it would be awesome to just have local Super Maven. That'd be great. I'd also love to know what the model architecture is. Ice cream. I actually had forgotten that this was going to have cross terms. I thought this was going to be like a super trivial operation. Well, we'll get this implemented and checked hopefully tonight. Does anybody know if this is correct? This can't be that uncommon of an operation. I wonder if that was in part due to my my message. Because I like bitched them out a whole bunch, I remember. Does bitching on the internet actually work? I mean, this post didn't even get very much, yeah, this post barely even got any attention. Maybe one of them saw it. Oh no, you know, it was probably this one. It was probably Ironclad. Literally the only usable AI plugin. So I think then the only thing is we can test this pretty easily. And actually, it's pretty quick to get a gradient check on this. I don't even think there's anything that can be numerically weird here either. So then the only thing that's going to be a little tough with this, there's one thing I don't know how to do. Fun fact, I never learned CUDA. I kind of just started writing it. I just sort of went, it's just C that runs on your GPU. How hard can that be? Well, there is some extras to do block reductions and such, and when you do operations that require accumulations like this, you have to do block reductions. So I'm going to finish this ice cream. I will answer any random RL questions in the process, and then we're going to implement the rest of this kernel, and we will see whether I can at least get a working version of this, I can time it, and then I can see whether it needs block reduction to actually be fast. Which I think it will need block reduction. I'm not positive, though. I mean, it's such a tiny kernel, right? It's almost, like, impressive how slow Torch is. It takes the same amount of time to do the frickin' RMS norm as it spends in mapmol. Welcome, geography. So that makes no sense, right? Like, literally, this was the profile from before while I'm eating this. Take a look at this. Okay, look how ridiculous this is. Okay, not the same amount of time, but still look. 96 seconds in here. And I think this was without RMS norm. It was like 80 seconds, 80 ms at some point in mol. The easier one to see is it went from 410 ms to 540 ms with RMS norm. So, like, 25% overhead of the entire CUDA time just for an RMS norm. Crazy unoptimized. I mean, like, I'm trying to think what it even is possible. It's probably just PyTorch doesn't bother to do a block reduce, right? That's what I would imagine. Because I don't know how else you make it that slow. So if I implement this kernel, and the naive version is about the same speed as the PyTorch one, then I'll know that's how they did it. That would actually be kind of funny, because that would mean that my absolutely newbie level of, CUDA engine that I'm doing here already matches the PyTorch backend for this op. Wouldn't be surprising. I mean, the thing is, in their mind, right, this op is like never the bottleneck. But you shouldn't be writing your generic tensor processing framework assuming nobody's ever going to train networks that are smaller than hundreds of millions of parameters or whatever, right? Like, Torch has been around for long enough as well that, like, people were definitely training way smaller models when it was in its infancy. And somehow it was just always slow. I'll look at this in the meantime, see if this makes sense. You have to sum up. How is it that you do this when they're cross terms? You have to sum up the cross terms, right? Gain through the weight. RMS without the weight has gradient, well known. 1 over R, G minus G, XG. Okay, that looks closer, right? That's like something I would believe. Substitute X hat equals X over R. Then it simplifies to that. Hmm. Welcome, everybody. Halfway done. So provided this gradient is actually correct, this should not be that bad. If this gradient is wrong, then I'm going to have a pain in the ass attempting to do basic calculus and failing for an hour, most likely. We got like 15 people watching now. Come on, anybody know? Somebody at least has got to be fairly recent on calc. If you asked me when I was 18, I could have done this no problem. Nah, bro. I mean, if you go check, I say take CS 231N in my guide, right? If you do 231N, you'll do this. This is like marginally harder than high school calculus. Circle dot symbol, it's just element-wise multiplication, dude. Hadamard product, just element-wise mul. If you don't want to see that symbol, you just write the grad with respect to xi. So if you just did dl partial L partial x sub I, then it would be wi times gi xi wi gi over, this is the RMS norm, and then this is the RMS norm cubed, and this is xi. They, like, nowhere near as fancy. And then if you do that, then it's like, I mean, that really is just high school calc. Now, the only thing, which is the thing that I totally forgot about that doesn't come up very often, because it only happens when you have ops that are, like, not element-wise like this, when you have summations and things that like this, you get these cross terms, because you have to take the partial, right, with respect, where is it? Partial, yeah, so partial yi with respect to xj. If I equals j, that is the single variable case. But you also get derivatives of each term with respect to the other terms. You end up with these cross terms. So I was looking at this, like, where the heck did the cube term come from? So that's where the cube term, probably this. I'd expect this whole thing comes from it. Maybe not. Maybe there's something factored out, but I think probably that. Actually, exactly that, right? WG over... Oh, no, there is one other term. Yeah, there is one other term that gets grouped, it looks like. W over this minus... Yeah, okay, so there's... Alright, it's a little more complicated than I expected. Whatever. This is what happens when you don't do derivatives for 10 years. Funny enough, though, like, the one course that actually has some math ends up being the one piece of math that's actually useful. Because if you know this stuff, right, like, this is honestly the hardest part about writing your own kernels, is that you don't have autograd. So, you know, it's the combination of you're writing low-level error-prone code, and there's also some, like, kind of real math involved. Math, any, like, math person will tell you that this is basic shit, but... I mostly write code, so not so basic when you haven't done it in a while. I mean, just basic stuff like I can't even if this were single variable, right? I can't take the gradient of this quickly by looking at it. It's like square root. It's like 0.5 times 10 times wait 0.5 the power of negative 0.5 of what do I do with this epsilon in here? Does it stay? I forget. And then this gets multiplied, and then this is what the heck is this? This is 2 norm, so this is another square root, so this gets another inner like I can't take the gradient of that looking at it. I don't know. That one, if you'd asked me when I was 16, I could do that. Oh well. I'll go do a little refresher at some point if I end up doing a ton of kernels, but I think we're only going to end up with a handful of them for this release. And a lot more of the effort is going to go into the optimization of perf. All right. Let's get started. Chain rule. Yeah, I know it's the chain rule, my guy. The whole freaking, like, that is the entirety of backpropagation is the chain rule. That doesn't mean I remember how to apply it to individual specific ops. All right. Let's get cranking. Okay, so W times G in norm minus X times, why is that parenthesized? Yeah, that's the funny thing, right? It's like a lot of the math that you end up actually needing and is useful is relatively simple math. Try it out. Okay, so now let's figure out. There are like 10 dot product notations. There are 0 dot product notations here. What? This is all element-wise. Oh, yeah. Well, excuse me for thinking you were talking to me on my stream. Output buffers. Adds buffers, okay. Hang on. Output. Out. Wait, no, not grad out. Grad X. Good. I haven't read it yet. It looks insane, which is cool to see that Forrester is not like just gone with the crowd. Math stats to understand ML models. Well, you sure as hell don't need stats. You need your pick of stats in linear algebra. You can kind of write everything one way or the other. Yes, dude. Literally, the RMS norm op alone is causing 25% overhead. I'm not joking. I have a feeling that I'm going to see this. I'm going to time this versus their implementation. I think what's going to happen is I'm going to match the speed of their implementation with this because they didn't do a block reduce. I think they just did, like, you know, one thread over the entire hidden dim. Oh, that multinomial BS is getting, like, crushed. I'm not dealing with that shit. Like, we're writing a kernel for that too, I'm sure. Speaking of which, I just dealt with a bug with that implementation that you wrote yesterday. Ah! That thing propagates nans in a really weird way. What did you do? If you get nans as inputs in your thing, it will sample invalid actions. So it turns out this was the thing that was causing invalid actions whenever people were getting weird runs. Part of that implementation was removing all of Torch's safety checks for speed. Uh-huh. Well, you don't need to have NAND checks everywhere, but there do need to be checks to make sure that you do not crash the execution of the program if you get NANDs. And that one can crash the execution of the program when you get NANDs. That was fun to find out. Your program is bad and should feel bad? Uh-huh. So, like, all of ML, then. How much ML is LSTM necessary? Yes, that's not very much ML. That's like one course, dude. And LSTM might not be necessary very soon, because we just got soda without an LSTM. Holy, look at that. 8.9. Mingru. Which is what we're writing kernels for now. A fast Mingru. Don't confuse DRL with RL. Everybody means deep RL. Yeah, Mingru works. Mingru's a bitch, though, because it's only useful if you have kernels. Like, you need kernels to make it useful. I got the main kernel, like, good today. Well, it can be way faster than an LSTM with kernels. But if you just implement it in Torch, like, you're gonna spend all your time in this stupid scan operation. What will it take to solve 100%? To solve neural MMO 100%, probably Puffer 5. Tech to be there with it. Yeah, and I couldn't find any decent kernels for it either. Like, it took me probably 3 days of fiddling with these stupid kernels to get this to work. total pain in the ass. No, we do not want... This is gonna be B times... T total. Because you cannot paralyze... You can't paralyze this. Yes, exactly. You have to calculate the derivatives by hand. That's why it sucks. So we do grid size. Grid size. Block size like this. This is, oops, RMS norm. Oh, really? You think so? Go ahead and try it. Tell me how much fun it is. And then, when the LLM that you're not using works, and some other asshole recommends you try a different LLM, go try that one and see how much fun you have when that one also doesn't work. And none of them work for 6 hours straight. And then eventually you just have to figure out how to do it your damn self. Big what? S word. The LMs are shit? I'm allowed to say that. Oh, should. Nope. The correct thing is, in fact, that the LMs are simply shit, and the people who think otherwise are getting replaced very soon, because they didn't do any thinking to begin with. I'm writing kernels, this is obviously going to be slow. It's a combination of very high precision, but also, like, there's a ton of boilerplate that you just can't get away from cause CUDA. I hate boilerplate, but what do you want me to do? Okay, there are the launches. And now, we write the module. Oh yeah, this is a great time to mention for folks here, because we have a lot of folks on at the moment. If you're interested in my work, I stream all my dev. I build the fastest open source reinforcement learning library, Puffer.ai, demos that run live in your browser. Feed the Puffer a star, helps me a ton. Everybody's on Discord if you want to get involved with dev. A lot of it's much easier than this. And you can follow me on X for all my research and educational content. Back to dev. Somebody's watching me on a flight. That's funny. That is funny. When you have to do template for every argument, I'm deleting these templates, my guy. I am straight up deleting all the templates when I'm done with this. We're going to support one type, and everybody else can fuck off. I'd like some CUDA practice. Ooh. What kernels do I need written? Well, if you would like to figure out why, because I'm not going to get to this one for several days, man. Loss. All right, so this kernel here, I have this PPO fused loss function. It fuses the entire PPO loss function. It passes numerical tolls pretty well, but it crashes training. So if you can figure out why it's numerically unstable, that is kind of the core of what I've found lately. Actually, like, getting the kernels to pass numerical toll, not that hard. Getting the kernels to be numerically stable, very hard. First time watching, loving the home gym. Thank you. What does crash mean? When I do, if I run this, I have a version of this basically, like, you can use, I'll make sure it's clean by tonight. But yeah, you can just, like, train breakout with the C version here in 4.0, and it works. But when I use the fused PPO loss, it doesn't work. Even though it passes, I have this this grad test, and, like, you can go enable grad test for whatever, and it looks like the gradients are good, but then it doesn't train. Bounty time? Yeah. Yeah, I tried FP64. I FP64'd everything, actually, as a default, and then I just got the fuse kernel back to FP32 stable today for the parallel scan operation. How do you test if it's stable? It just has to train. There's no other way to test stability other than does it train. All right, so what we want to do now is this operation. I'm just going to copy this whole thing. This is how much boilerplate there is for reference with CUDA work, because you need the kernel, you need the launch, and then you need the torch binding. It is a pain in the ass. Hello from JSOL on flight. Oh, is that you? Hello. Funny. I'm surprised the Wi-Fi works for live streams. You got Starlink on there? Autograd context. Do we need context? I don't think we need a context variable, right? Oh no, you do need a context. That's default. Yeah. BCC. You're free to try it. The other thing I really like about putting things into single kernels, it makes profiling much easier. Because it takes the time from, like, all the little individual ops that are annoying and it just puts them in your custom kernel. And yeah, you could figure out how to group things or whatever, but like, it's so much easier to just see like time spent in your small number of custom kernels. Way easier to optimize. Right, so this is where we need Nsight Python profiler. No, I did not see that. I've just been using Torch profile. Okay, so this is gonna take X and weight. Does it need weight? Wait, how do I handle stuff with a weight? Do I have any kernels with learnable weights? I literally don't have. Ooh. Well, I mean, I can put just. I can do this for now, right? Output is going to be same device and type. That's correct. And we need a buffer, right? What was the buffer called? Inv norm buff. And this one is just going to be this size. And now we actually need to go double check the arguments. This has no epsilon at the moment. We should add that before we forget. Out.dataPointer in norm x and weight. Static cast double epsilon. Alright, so we're gonna just pass epsilon as well, yeah? Do else if. That can autocomplete everything, yep. Fine. And then we can just set else we don't support it. Cool. So next, save for backward. Right. So all you need to save for the backward pass. You'd save X, right? And you save inv norm. You need to save weight. Weight out and inv norm. We don't need this nantinum. And we have the output. Cool. Next, we need to get the backwards pass. We know what these first bits are going to be. Let's fill this in. X weight out and inv norm. Get grad outputs. Dot contiguous. D type. Del B, T, and H. The sizes. And then we need auto grad X. Auto grad weight. Let's go see how I specified the launch args here. So RMS, I know that I did the exact same args for the backward and for the launch. Look like this. And this just has to be pass grad X, weight, grad out, and inv norm, X, and then where's it? Static, cast, right? We're gonna add epsilon, T, H, B. Cool. And I have to remember to add epsilon before I mess this up. And this is not launch fuse scan anymore. This is launch RMS norm. And let's just make sure this is line by line the same. See, it still tries to mess you up. Form. Okay. Have you ever tried writing tests? Yes, dude, I have those. It turns out there are things that you cannot test. There are many, many layers to CUDA hell. And then we need grad log coefs, grad log values. So I don't actually know how this is going to work because it's a learnable param. But we'll try like this. Let's go add this epsilon in before I forget. Oh yeah, save for backward. Let's just add eps. Can I not do eps? This is probably a tensor list, right? I think one of these casts is screwy, but whatever. We'll figure that out shortly. Let's just get double eps. And here we'll get double eps. And you literally have to add stuff in like 6 different places. Very annoying. I tried to figure out a way around this, but like there are actual CUDA compiler limitations that make it very difficult. And if you go look at like the solution that PyTorch even has, it sucks. And it's really not a nice way to just avoid all this boilerplate. Okay, so this is an end-to-end version. This is missing this. And you did not pass the weight back, did you? That is a problem. Yeah, this has to be weights. What color theme is this? There you go. It is my personal color scheme. I made this. This is the whole config file. There's not much in it. I'm glad you appreciate it. I've gotten many complaints about this color scheme, but I like it. On the flight, setting it up. I'm mad lad. That's funny. Alright, so this is not gonna compile, but we'll fix some errors. What I do here? Fix some errors. He is unidentified. This is not how you pass, oh. What? Yeah, I just put this here and forgot to delete it. Also, I forgot to add a autograd wrapper to this. See, this is the part that I hate the most, is the PyTorch wrapper binding shenanigans. Like, obviously the numerics are hell and stuff, but like that's kind of skill issue. This is not skill issue. This is just awful, awful code. And nothing, like, literally impossible to write anything better. Or not anything better, but anything good. Like, architecturally crap. What's the main reason? What alternatives? Jax? Terrible. Tinygrad? Better Jax, but not what I want. Anything else? Non-existent. Torch is also the one that everybody expects you to have. Dude, I hate Jax. You do not have to learn Jax for Majoko either, you know, like... You realize that you can just use Jax with PyTorch training code, right? You can keep the tensor on the GPU and just turn the Jax tensor into a Torch tensor. DeepMind suites? Well, DeepMind suites suck. So, like, what's the point? You're not going to be able to do anything because, like, those DeepMind M's are so slow, they're unusable. Oh, yeah, I guess they did make... I forgot they did the Jax version of them. If you have to do control, then I guess. But, honestly, Jax training code is just, so bad. It's like classic Google, we are very clever, let us show you how to build things. They build something terrible. No instance. Inf data. MJ warp. I mean, that's still not a reason to use it for training code, right? I honestly think that the way to go for training code is going to be... It's going to be closer to what I'm doing here, which is just that we end up getting ourselves a collection of kernels, like fused kernels, and we use those with basic Torch code. Like, you'll be able to even use these with the Python Torch API if you want, and it'll still be way faster than anything else. Wouldn't Warp be compatible? Yeah, Warp will be compatible with Torch. I mean, don't use it with Jax, right? Like, I don't know what tensor backend they're gonna ship it with, or tensor integrations. But, like, that shit should not be hard. Well, shouldn't be. Okay, so this is some, gross C++ syntax. Oh, well, it's going to be on the GPU dummy. I'm just gonna see if I can figure out from this one small thing. CPU scalar tensor. Dot item. Okay. Yeah, that's kind of obvious, right? So I can just do torch.tensor of apps like this. And then what is it? Dot item. This like weird syntax. This is double. This is eps. Eps. See how this goes. Total. Yeah, we just place this for T. Welcome, Hyper. Eek, what's this? No suitable conversion from disgusting C++ thing to disgusting other C++ thing exists. Fun. Fun, fun, fun. What are we doing today? We are working on some kernels in the CUDA mines. There are several kernels that need to exist and to be fast for PufferLib 4 to be good. I am currently working on them. It is hard. Log ratio. Warning. Wait, one error detected. Wait, where'd my error? Huh? Oh. RMS. This is key star. And tomorrow, I do not work on kernels. Tomorrow I lift weights all day. That'll be good. I'm just gonna lift weights and weights and weights. This actually built fuel. There we go. Yo, what the fuck? Did I paste the wrong shit? Oh, I pasted the wrong thing, didn't I? I must have. I'm confused. Did I paste the wrong thing? Oh yeah, I just pasted the wrong thing. Perfect. What's this? I don't know about this one. Use NeoVim. Yep. what you find useful usually. The exact setup that you see me using here is what I use for everything. What's the prototype for this? Oh yeah, it's the impl. Okay, so it would just be like this. Explicit impl. It just made this shit up. Get rid of this. Yeah, this is just like torch bullshit. Okay, so this is RMS norm. Okay, I mean, that does build. So, I guess we... do this, right? The heck is this? Ugh, Yeah, I hate this shit. We're gonna have to really figure out how to make, like, Torch go away and not suck so much. Huh? All of? The heck did this bind? Wait. Well, I've officially managed to listen to the same song so many times that I've noticed some very small background noise in it that you're not supposed to notice that has annoyed me. Alright. How I have it. That's how I have it. Oh, module? Wait. Yeah, like this. I see. That's annoying. Company profit. Yep. We provide mostly it's off of custom sims. We do some prio service stuff. Pretty soon that's probably only going to be for existing sim clients. Or like new sim clients, whatever. There's also like R&D and other things. Mostly sims these days. I really focus the vast majority of my time on core research. And then we do like some business. And though, I mean, presumably, right, the prices will just go up as Puffer gets to be more and more ahead of everything else. Like this update was so much work, but it's gonna make Puffer so fast. I mean, kind of my goal this update was like leave no stone unturned, really aggressively optimize perf, see how fast things can be. RMS norm. Really? So weird. This honestly feels way worse than the CUDA because this is just like straight bullshit. Honestly, for now, I don't feel like dealing with this, so I'm gonna do it this way. Like, honestly, what the fuck, PyTorch? Maybe it'd be a better library. Okay, so there, we can do RMS norm. All I have to do is allocate the weight. Yeah, this will be easier as well, won't it? So dead tired, man. That's better. I want to at least get some version of this tonight. Half hour or so. Fuck is the error? Plan to hire people? I do, on a contractor basis. Obviously, only people who have, like, demonstrated that they can handle substantial RL projects in Puffer, though. Very, very few people qualified. Okay, cool. So now... Perfect, now we can do this. RMS norm takes 2 positional arguments. Good signature. What normalized shape, weight, EPS. Okay. That looks like a legitimate mess up on my part. Come on, let's get this thing tested. Alright, that builds. Max diff nan. Cool. Lovely nan diff. Out in norm. X. Okay, so what do we parallelize here? We get batch times t total, right? Grid size. Okay. This index is responsible for all h. I don't know what this b and t is. Oh. I think this is probably wrong, right? How do I do this? Kernel. I think these indices are wrong. ETH. Yeah. Yeah, it's like this, right? Norm this other dim because it's, yeah, the parallelization dim is the other one. T. And base offset. Base b times this. Base offset. Index. Let's see about this. Indexing is a little iffy, right? Wait, batch times plus. I think that's actually fine. Max diff is nan. Okay, so why the fuck did it do this? Oh, you didn't divide by h, dummy? Ah, it's like this. This. I missed one thing. I missed, I had the weight on the wrong dim. Diff is 11. Okay, so we get a real number now. Six. Was val. Val times RMS. Correct to me. Boom. Correct kernel for the forward. Returned an incorrect number of radians. Forward's correct. Forward signature has 3 inputs that required radians. I see. I don't need double F's in here, right? Wait, no, the forward has 3. So you gotta return torch tensor. Grad, wait, grad, okay. Grad F's. Grad F's. That's a no grad. Can you do this? Oh. Try this. Okay, so the kernel breaks, but that's fine. Inv norm. B and T. Fine. Yeah, so this is completely wrong. Ugh, how do we do this? I think grad X is correct, isn't it? No, no, it's not. Yeah, it's completely screwed up. Okay. Where was my original, yeah, where was this? What? This is Hadamard product. That doesn't make sense. Oh. This is dot product. This is Hadamard product. I see. Okay. So then you have to do, for dot product, you have to do a loop over H. WGR. Yes, I need the... Okay, hang on. I know how to do this. Tired. I'm gonna try to not let it mess with it too much, but I need the indices. I'm too tired to calculate the indices manually. Not what I asked for. Yep, not what I fucking asked for. Fucking, I'm doing it myself. These models are dumb as shit. Get B, T total, and H, right? Just a percentage. It's literally just a percentage. We don't need any stupid models. Did IDX over H? No. IDX percent H. Okay. And then the norm index. Is divided by, right? Okay, so now we have to do 4. And then from this math, I should be able to do it. This, right? In RMS3. RMS. So, right? This does not change. Does this change? RMS. No, it doesn't. So then what I get to do oh, this would imply. Yeah, this would imply then that we have to do the same kernel structure. Good. Okay, we'll do it this way. Okay, we'll do it this way, right? Form buff of index. You get this one. Okay. So wages of dim H. Grad X index is plus H weight H grad how is that a Hadamard product? Minus float X float W RMS that's a dot product. Now let's figure out why this is stupid. Oh. It is? Hmm. Now I'm confused. I think you want some of this, but I actually think I had the loop structure correct before. That's right. Okay, so now what? This base address. B. Isn't base just 2%? I can just do percent base. This is, yeah, this is it. Base. What's wrong with my for loop? Eh? Just do float scalar. It's just a grad base index equals this is H index, isn't it? Norm index? No. Base. Oh, it's base. Base. Grad out. Okay, why is this not... What's this, this error real quick? Expected a semicolon, you dumbass. Full autocast as well. I don't think I used eps anywhere. Okay, well, it runs at least. Yeah, this is wrong. Yeah, this is completely screwed up. You don't need this. Make a little bit more progress and be done. What you'd like to do here, this is the scalar element. This is index. And what about grad W? One should be very easy, no? Just be this. And we break. Because this should be base. Oh. Shit, yeah. Gotta wait. This is actually a very tricky kernel. I'm gonna have to finish this tomorrow, but yeah, there's some tricky stuff here, guys. It's like I sit down to write what I figure is gonna be a very basic kernel, because it's like a 3-line operation, and it turns out it's a very, very freaking complicated kernel. Wouldn't you know it? This is why Autograd exists. Too bad it is slow. Maybe this one I shouldn't have done like this. I don't know. But the way that Torch has their kernels, they're very, very hard to just, like, use and build on. Anyways, we'll get this finished at some point soon. It really just feels like this is a hole you can pour unlimited time into. I think we'll do this one. We'll see from there. I gotta get some rest. So for folks who've been watching, thank you for tuning in. I will be back live tomorrow. Nope, tomorrow's Sunday. Tomorrow I lift weights all day. I will be back live on Monday. If you're interested in my stuff, everything's live. Puffer.ai. You can watch agents playing in your browser. These are live RL agents. Like, you can. This is me playing, taking over. This is me with my hands off now that can actually play correctly again. Feed the Puffer star helps me a lot. Is it cold in your gym? Absolutely. Join Discord if you want to get involved. Other than that, follow me on X. We are doing quite well on here lately. Almost at 25K, and all the educational stuff is on here as well. I don't know what this is. All right.